Hi, and welcome to class 3 of our VR bootcamp. So what this is going to do with this week is we're going to actually not be looking at the Samsung, which is great. This is a great unit, but I actually want to use the example of the HTC new Valve thing. And what I want to do is discuss the issues around real-time rendering, give you some sort of background on that, and then a test case. We're going to talk to a really good friend of FX, Guide and FX PhDs. In fact, we've known him for years, Michael Henson. And the reason I'm doing this is really because I want to address a couple of things. The primary applications at the moment of VR are either mobile, which is what the Samsung is, which is either playing back or doing some rendering in the technology of, say, the phone, or we're doing something with a high-end, super powerful PC. And so we're doing something like that. We might be doing something like the Games of Thrones experience or the Interstellar experience. These are ones that are done by Framestore. And they all use these high-end PCs. Why is that? Well, it's because they need the performance to pull off what they want to be able to do, and so they have these jacked up, wonderful PC units to run them. It's quite a different problem from what's going on here, because these experiences, these specialist installation setups, require a lot more computation than you can get out of a mobile app. So what I want to do is show you why it requires the power in part one, and in part two, look at what might be, for example, a specialist application that would make a lot of money that would want you to do that. So in other words, in this course, we're not going to teach you how to program hardcore, high-end hardware that isn't even released yet, but we will be able to publish as much as we can about what's coming and how it's going to be, so you can think about it. But at a 100-level course, you just need to know what the issues are. And of course, the gear isn't out yet. In fact, the HTC is not going to be out until later in the year, and that's the developer kit first, and then the final one at the end of the year. And as I said, we're going to be taking some stuff that was published at GDC by the Valve people on the makeup of that, and then talking to Michael Henson, who literally was a friend of ours from before there was an actual FX Guide or FX PhD, literally from the earliest days of discrete logic. Really, really bright guy. Okay, so the Valve HTC unit is been discussed. It was launched by the CEO, Peter Hsu of HTC a little while ago, and took the market by surprise to a certain extent. It's a really clever thing, and something that makes a lot of sense. I'll discuss it a little bit, probably discuss it much more later in the term, but it's a really clever move by these guys, and a lot of people have money on this being a heck of a winner, and I'll discuss that a little bit more in a second. Now, there are a whole lot of rendering issues when you're dealing with any of these type of systems, and this is quite independent. It's just to do with the nature of how stereo or whatever works. So stereo, be it in a mobile device like this or HTC, is designed from an idea of two eyes, right? My two eyes, there's two eyes, right? And if you're in the cinema and you're wearing something in stereo, it assumes that your head is pretty much horizontal. Okay, so my head is like this, and I'll look around a bit in the cinema, not much more than that. If I've got VR goggles on, I'm looking around a lot, which makes perfect sense, right? But I'm still on this plane of stereo. But when I start looking up to the roof and turning around, or looking down and turning around, stereo kind of breaks down. It's effectively the same as if you had the headgear on and put your head on the side. The stereo assumed, so you're doing live action, if you'd set up a bunch of stereo cameras, they assume this axis for stereo. It's not like they can do this because you've got, as in with the cinema case, two lenses that translate to two displays that shoot this way on the same level plane. They aren't designed for this or this, so it's a bit of an issue, right? Now, if you know what someone's head's doing, that's fine, but if you want to have them so that they can go any which way, you get into a lot of problems, and so that's a real complicated issue. And in fact, most people gradate the stereo off, so at the top there is no stereo, and down there's no stereo, and the stereo is in a band that fades out from the viewing horizon. Comping is a really big problem for a number of reasons. Review and playback is a problem, and when we do a post-production pipeline, as we're going to be doing this term, we'll often show you a longitudinal sort of format. So let's have a look at this one. This is a 360 that I did in the lobby of ILM. So this is the publicly accessible part of ILM. I haven't broken any laws here. But you'll see my hand at the bottom of frame is just enormous. Because when you spread out a spherical mapping, you are basically taking at the bottom of the sphere information and you're stretching it out for the entire horizontal. So that's, obviously 360 degree around, and the bottom of a 360 when it's in a sphere is almost a point. And so my hand becomes this enormous thing across the bottom of frame. And it's not a mistake with this particular image, it's just how it is. So a 2D mapping of this becomes a problem, because if I was to paint on here, my paintbrush would change size between the top and the bottom of frame. And of course, then I have to do it in stereo. So I have to paint, but I'm in different places between the two eyes. And all of this is just with live action. So none of that changes when you go to rendering stuff in 3D. So there are, like a truckload of problems with the nature of VR to start with, and then we get to the specific problems of rendering. So at GDC, I think it was, they launched the HTC and it's the Vive, the combination with Valve, and it's a really bright partnership, because if you assume for a second, and you'll see why, you really want a powerful PC to be able to run some really interactive stuff with high-end PC, high-end graphics cards, all that kind of stuff. That isn't something that everybody has. You want to play back some stereo live action? Yeah, put my phone in this, good to go. But if I want to be interacting in a rendered in real-time world, I'm going to need a lot of grunt. And what is a group that happens to have a lot of grunt? It's the gamers. And the online gamers that are attached to Valve are a group that already pay money, already have a credit card system in place, are used to downloading from you, and have high-end gaming PCs. Not only that, but the Valve guys actually worked with Oculus Rift in the early days on head tracking, so they know a lot about that. There's a huge amount of infrastructure there, and Valve are just really bright guys. They've proven that time and time again. And so they're developing a VR API and also a cross-platform open VR platform, and this is what they were discussing. Okay. The developer specs, because it isn't released yet, as I said, it's coming out in the spring for the developer edition and the consumer one at the end of the year, has hands. In other words, it can actually see where your hand devices are in your space, which is a big, big step forward over other things. It also has very low persistence and a global display. So it lights up all at once and it doesn't light up for very long. The reason for this is the lit up picture is, if you like, the moment that I'm interpreting that movement. As I'm turning my head, if I see this part of the room, if I keep moving, that part of the room should have moved with me. But if I hold up the image in my head display for very long, I'm getting an image that's no longer valid, right? So what I really want is to be correct image, go away, correct image, go away, correct image, go away. What I don't want to have is correct image, it's not correct, but I've still got it up. Now it's correct, oops, no longer, but it's still up. And now it's up again. Does that make sense? So you want to have in a frame time, which is already not a normal 24 frame, but in a frame time, you don't want to have the image up for very long. You have a very short persistence, and you want to have global, effectively, display, because you don't want to have rolling shutter type stuff. And this is spec'd at 90 hertz. So instead of 24 frames a second, you're doing that 90 times a second. So you've got 11.11 milliseconds to get it up, no rolling shutter. And then in terms of the resolution that they've published, it's 2160 by 1200, which is to say 1080 by 1200 per eye. So that's kind of interesting. The trouble is you actually have to render more than the resolution, because you're going to do some warping to it to get it into a VR headgear. And so as a rule, you do 1.4. So you do over rendering effectively, and that's what goes into the back buffer. So you need to render bigger than the actual res. You're going to have to warp it, you're going to have to render it very, very quickly, and you're going to have to render it in such a way that you can do it 90 times a second and sucker that one in really, really quick. That actually works out to be 2,540, thereabouts, shaded pixels per eye. The other thing is the field of view. So in any VR headgear, we want more field of view as possible. I remember in class 1, Mark Bowler said, I said, how much field of view do you want? He said, well, when you have a lot, you want even more. I mean, whatever you've got, you want, right? So I have quite a large field of view. That'll become important in a second. So 110 degrees. And as I said before, it tracks the room and it tracks your hands in the room. So if I was to reach for something in the virtual world, where I perceive my hand to be is, of course, where the object is in the room as well. And those hand trackers are a very, very key piece of technology. So a lot going on. Okay, so why the 1.4 back buffer? You have the lenses that are warping, and you are producing an image in the headset that isn't just a straight view. Okay, now, there are also various things that you're doing to compensate for the fact that the warping would otherwise, I guess, produce chromatic aberrations and sort of problems, because there's, like with the sphere problem I was saying before, there's sort of pinching that's going on around the edges. The middle of what you're looking at in the VR window is pretty normal, but around the edges it's kind of getting compressed and bent in that classic sense. And if you take all of this into account, there's a better way of thinking about what you have to do in VR, which is just to combine all these numbers together into shaded visible pixels per second. So I'm saying, rather than talk about just the frame rate, the number of pixels, whether it's stereo, everything else, just say, could we get one number, and we can have a think about how hard that is to hit that number. If we combine all those numbers in terms of resolution, hertz, the overshoot for the warping and all that kind of stuff, what do we get? Well, on an older console, which was 720p, obviously mono, 30 frames, that was 27 million pixels per second. That was like the last gen console. If you go to 1920 by 1080, 1080p, 60 hertz, so kind of, reasonable new console, pretty impressive, 124 million pixels per second. Now, the reason that's a lot more is that when you go from 720p, you're going up in resolution both horizontally and up in resolution vertically, and of course you're doubling the rate from 30 to 60, right? So it's, literally an astonishing kind of 5 times more. All right, now let's go to a PC. So I'm going to a computer screen that's got a higher resolution screen than my telly. My telly was 1920 by 1080. My computer screen is 2060 by 1600, still at 60 hertz. I'm now at 245 million pixels per second. Those are shaded pixels. Okay, now I go to 4K. When I go to 4K, that's even higher res than my PC. I'm now at 4096, 30 hertz, 265 million pixels per second. But when I go to VR, with the specs that the HTC guys have published, Valve has published, it's 1512 by 1680 at 90 hertz. So you actually are hitting 457 million pixels per second. And I think this is a really key graph, because only when you see that, you start to realize why the VR stuff is such a hard ask. The reason why, when you want to have a dedicated system, you want to have a dedicated PC with a high-end graphics card with a Titan X in it, is because you're trying to hit this number. Well, as I'll say in a second, you can actually get it down to about 375 million, but nevertheless, even at 375 million, it's sort of worse than a 4K monitor running in real time at 30 hertz by a factor of 2. So, it's just an astonishing amount of stuff you've got to throw around. And then, the number one criticism I personally have of VR is it's not high enough res. So like, people literally kind of cry when you say that, because they're like, you've got any idea how hard this is to push around? Okay. So, how do we trim it back? I said a moment ago you can trim it back to 375. It all comes from that warping I was talking about. So this is the warped view that you have when you're looking at a VR image without the optics of the headset. And of course, if you were to measure it somehow, you don't get to see the corners because your eye's around. So you basically get to see this much of the picture. And if you were to compare those two, there's a bit that seems different. Now, it's not a lot on the warped view, but when you unwarp the view, it's this much that you don't have to render. And so, in fact, there is some areas of the screen that no matter how hard you try, you won't see in a headset. So people are just not rendering them. So there are some tricks to be had to kind of produce these two images that the HTC would actually use. And this is very specific to the HTC rig now, right? I mean, it works in all rigs, but these numbers that I'm talking about are all HTC numbers. This particular picture is only relevant to an HTC. There would be another similar picture for an Oculus Rift. And just to highlight some of the other problems you've got, because this will come up, you'll hear in the Michael Henson discussion, the fact is that you've got these incredibly short periods to render the frame, to display it in the headset, but you kind of want to know where my head is going to be for the next frame, because what you need to do is work out where the game engine needs to be, then fire a render, have the render, and then load it in my headset. And so in fact, you actually have this kind of frame delay. So what happens is you say here, I want to render this. It takes time to render it, and then it shows me at the end of the VSync. In other words, it doesn't, and I remember it flashes it up. It doesn't flash it up at the beginning. By the logic of this, it flashes it up at the end. And so you've got basically 2 frames from when it says go render to when I see the picture. So 2 frames doesn't sound like a lot, but if I'm turning, I can work it out. In fact, I think they worked it out to be about 5 degrees. If I'm turning at a rate of 5 degrees a frame, I need this to be right. If I'm really, really fast, it's kind of blurred anyway and I don't really care. But up until that point, I certainly do. So you have to predictively work out the frames. It actually gets worse than that because you have to solve the game engine, then fire the render, then have the render, then load it, and then up. So it's at least a couple of frames, if not worse. Now, remember I said that aliasing was a big issue that had to be solved. And the reason for this is pretty simple. When you've got a VR headgear on, whoever it is, you don't stop moving your head very much. Now, we're accurately tracking your head, so even little movements of your head are causing things to happen. And if there's any problem with aliasing, you're going to see it, right? Because you're constantly moving. So instead of being rock solid and steady where it doesn't shimmer, if you move a little bit and things are aliasing, they'll really, really show up. Same reason, similarly, grads are really bad in VR and you sort of do things to those. I'll mention that in a sec. Okay, but if you're watching a TV and you're sitting there and the TV's in front of you, what's your field of view on the TV? It's like 50 degrees, right? Like it's 45, 50 degrees because it's sitting in front of you. It's a big monitor, 30-inch kind of monitor, but it's still sitting here in front of you. It's not that bad. But what we've got in VR is 110 degrees. Not 180, but it's 110. And so if you think about it, those pixels are distributed over a wider field of view. So for every sort of slice of that field of view, you actually have less pixels that are going to be able to solve the problem that you want. This is a pretty unique VR problem. It's one worth getting your head around. So on a 720p monitor, you get about 25 pixels per degree. On a big high-res computer monitor, 30-inch, you're going to get about 50. But in VR, because we're taking our pixels and distributing them for this much field of view, any 1 degree is only going to give us about 15 pixels, allowing for, of course, the overshoot we mentioned before. So you need really, really good pixels for it to work. So you need a lot of them. You need very good quality. You can't have aliasing. You can't survive with things being locked off and not moving because your head is always moving. It's just terrible. You really, really notice scrolling and crawling badly. And Valve, on that example that you saw with the thing from Second Life, was basically kicking about 12 million triangles. So that's a lot, right? All right, so aliasing is a big issue. Over in Background Fundamentals, we've got a whole class that I'm doing on how they're solving this with normal mapping and MIP mapping, and it's really, really clever. And I totally recommend that you check that out. So there's a ton of hard work that has to be done to do all that. Why is Valve publishing all of this and coming up with these really innovative breakthrough solutions? It's because they really want this to work and they want it to be happening for anyone and everyone. And so if it was hard to do a high-end game, it's really, really hard to do a high-end VR solution. That being said, there are very big financial opportunities if you can pull it off. So that being said, and that is a kind of base work as to why the predictive stuff is required, why the aliasing is really hard, why knowing where your head is really matters, and also having some understanding of your orientation of the head at the horizon line. Let's now cross to my interview with Michael Henson as we discuss an application that could only be done if you could somehow have very dedicated hardware for each headset on somebody. Well, I'm joined now by Michael Henson. Michael's an old friend of ours. Thank you so much for coming in, Michael.
You're welcome.
So I was keen to get Michael along because apart from being one of the brightest guys I know, Michael was involved with VR very early on. In fact, way before Oculus Rift, you had real interest in stuff to do with using Silicon Graphics type computers to do stuff, right?
Yeah, back in the early 90s, I was involved with Silicon Graphics here in Australia, back when it was called Silicon Graphics and not SGI. And at that time, we were doing some work with virtual reality for sales centers, for selling bricks and tiles of all things. And I realized then that virtual reality was not immersive, and the technology that was around was not going to have the virtual reality be immersive, and the headsets were massive. And what I realized was that it was so constrained that if you could find an application for it that was equally constrained, there might be a use for virtual reality back then. And we were looking at putting virtual reality on roller coasters. It was not feasible technically back then, but it was certainly fun to think about.
Well, I think it's really great to explore a project like this one that Michael and I are about to talk about, which is sort of saying, what could you do if you thought a bit outside the box? But also the other thing about doing is, let's just get a chance to talk to you, because you actually were one of the original people to buy a Dev 1 kit of Oculus. This is before Facebook, right?
Correct. Yeah, so this is in late 2012, early 2013 from memory.
So before we get to the idea of the roller coaster, which I think is a cracker, by the way, what was the sort of the vibe like around Oculus Rift back then?
Oh, it's interesting because in some ways a lot of people didn't take Oculus seriously, because the very early versions of the Oculus Rift were very handmade. And so for people who were quite involved in the VR community in the 90s, a lot of people didn't take it seriously. And certainly I talked to some of the guys who were involved in a company called Virtuality in the 90s, and who were one of the only companies that looked like they were going to make money from virtual reality back then. Unfortunately, they didn't do too well in the end, but they certainly didn't take it seriously, because they thought that the problems that virtual reality had weren't being solved by Oculus. What they misunderstood, though, was that there was such a groundswell of support through the gaming community and other communities for what Oculus was doing, that sort of Kickstarter approach, where they got such support so quickly, meant they were able to solve all of these problems that people didn't expect them to solve.
So, of course, Oculus Rift, as we speak, have still not actually shipped a product. We had DevKit 1, DevKit 2, of course, we're now looking at the Cove. But if we go back to 1, when you got it, let's discuss now why were you getting it, and what was this roller coaster idea that you thought might be something that you could explore through the Rift?
Right, so what I was interested in was good commercial applications of virtual reality. And from a commercial point of view, it was all about finding a problem to solve and ensuring that the customers that we'd bring on would see value in that solution. And so from my point of view, it was actually an idea that I was discussing with a business partner of mine that I was going to throw away, that I thought was just too frivolous and not that interesting. But from a commercial point of view, it made a lot of sense, in that if you have a theme parks who have this very aging inventory and very expensive inventory of roller coasters, you can essentially see those as loss leaders, in that the roller coasters are the exciting thing that brings people into the theme park. People pay their $65 to $100 a ticket, and then 30% of the revenue in the theme park is food and beverage.
Wow!
But it's a big market. So it's around a $17 billion market. It's around 260 million people a year.
So hang on a second, just $17 billion for a couple of 100 million visitors to presumably things like Disneyland, Six Flags, SeaWorld, those kind of like
absolutely
big kind of, and these are really established companies, aren't they?
Right, and there's really two levels of theme parks. There's the regional theme parks, which I'd class Six Flags as a regional, and then there's a global like Disneyland and Disney World. And if you look at the amount these guys are spending on roller coasters, I think the latest Transformer roller coaster at Universal was a $92 million roller coaster, and there's two of them. So there's significant money being spent. So the commercial idea was really simple, which was for smaller parks, which were very reliant on their roller coasters to bring people in, as sort of their advertising to bring people in, is if they have this old inventory, then their choices are they can either knock the roller coaster down and build a new one, which will cost them $10 to $20 million for a regional park.
Yep.
Or they can try to refresh it by adding some useful stuff, maybe some video displays around the roller coaster, or
repainting it.
And so what we were offering them was, say, well, rather than spend that money or leave it as it is, spend a smaller amount of money with us, which is not a significant capital expenditure. We'll give you, say, 100 VR headsets and will give you 6 new rides, which will be the most exciting rides that anyone has ever done in their life.
Now, just to be clear about this, I've been on, like, say, Star Tours at Disneyland, and Star Tours is a simulator ride, and what makes it so wonderful, apart from the franchising and the connections with the whole Lucasfilm, now Disney proposition, is that I'm moving and I'm witnessing things in the room that are moving. So what you're saying is, forget the fact that the platform can only go up and down, like, you know, whatever it is, 20 feet in the case of Star Tours. I don't know what that number is, but it's something like that. I would literally be on a full flying roller coaster.
Correct.
And I'd be witnessing not California around me, but presumably anywhere you guys wanted to make me.
Right, and so the idea is that as you buy your ticket to get into the theme park, you'd be upsold to the hyper reality experience, and that would cost you an extra $15. You get an armband. When you get to the roller coaster, the operator sees the armband and gives you a headset. As you sit on the roller coaster and you go up the first climb, the interface would tell you what you're about to experience, and it'll give you a choice of, say, 6 rides. And so it could be the Yosemite experience. It could be the latest movie that you've seen experience. It could be the Eiffel Tower experience or the F/A-18 fighter pilot experience.
So let's say it's the F/A-18 fighter pilot's experience. I would have to say that if I get such a rush out of Star Tours because it does a bit of dropping and I felt a bit like this, if I was actually doing a 360-degree loop on a roller coaster, but I was seeing, you know, clouds and the skies and stuff, that this would be transformatively immersive.
Absolutely, and that's the key is... the key for virtual reality, from my opinion, is about ensuring this immersive experience. And there's certain things you have to do to have your brain absolutely believe that you're immersed in this environment. And as soon as you can achieve those things, it changes the game. And so that was what this was about, was saying, now that we have these roller coasters where we have a predictable path, and if we produce cinema quality graphics that's perfectly synchronized to your experience, the level of immersion will be so great that you'll have absolute belief in what you're seeing.
So let's discuss a few of those things. Let's discuss the synchronization. You're not talking about some spotty kid pressing the play button on my headset at roughly the right time. You're getting it much more precise than that.
Absolutely. So what we do is we build a model of the roller coaster, first of all, in a simulator. So we take the 3D models of the roller coaster, we simulate it, and we simulate what accelerometer, gyroscope, and magnetometer readings you get. And then once we have this model, we go and ride the roller coaster. So we'll ride it 10 times, and we build up a real model of what to expect in terms
from the data that you
data,
yep.
right?
Okay,
so we ride it with a particular sensor, which is similar to what's in a virtual reality headset. So now we have very good data about what to expect on that ride. And then what happens is when you actually ride on the ride wearing the headset, we're constantly looking at the information we're getting from the accelerometer and gyroscope and magnetometer, fusing that data together, and then we're comparing that to the model we have to be able to predict where we think you're likely to be so that we can have the imagery loaded up ready to go for very low latency. So it's about having it be accurately representing the G-forces you're feeling and have it be at extremely low latency. And in our case, because of the confines or the constraints of the roller coaster, we can predict several frames ahead as to where you're going to be and what you need to see.
So is there some kind of real-time knowledge of where I am on the roller coaster?
No, it's unnecessary. Well, we know that we can derive that information because we have all the curves of the expected sensor data.
Right, and it's on rails. So after I've had that loop, I'm going to have that one next,
Correct.
Right?
But it's even more than that in that every different roller coaster has its own profile of high and low frequency G-forces. Okay. So little bumps in the tracks.
Right.
So we see all those as well.
But now, the thing about the VR helmet is I've got it on. I'm not just doing this on the roller coaster. I'm looking around and I'm screaming my lungs out because I'm in an F/A-18.
Right.
How do you account for that? I mean, is it real-time rendering? I mean, how are you doing this?
Right. So, and this is something where we diverged a bit from what Oculus and the others were doing. So Oculus were very focused initially, at least, on games, on gaming. And in gaming, it's all about real-time rendering, trying to get the frame rate the best frame rate you can get with the physics you have, and with the limited field of view that you can afford with the hardware you have. With what we were doing, we didn't have to worry about that because we weren't essentially having to worry about real-time rendering, in that all of the panorama that we were displaying was known beforehand. So what we were doing is we were pre-rendering a stereoscopic panorama. And we can do that at whatever quality we want, at cinema quality.
Okay, so just to make it clear, if I've got, I'm going to use your pen if I could, if I've got my F-18 and I want it to make it look like I'm flying over the Grand Canyon, you would actually photograph the Grand Canyon.
Correct.
You're not going to render the Grand Canyon.
Yep, so what we'd do is we'd take something like a SenseFly or some other technology, we'd fly drones over the Grand Canyon, build up a sequence of stills, and so we could take it at the studio, create a full 3D model with high-quality photographic texture maps. And then we take the 3D model of the roller coaster, and we use that as the camera motion path in that 3D scene. But unfortunately, the Grand Canyon is actually really boring. I mean, there's not really much in the Grand Canyon from a roller coaster point of view.
Okay.
Right? It's beautiful to be in, but in terms of things to look at when you're flying through in a roller coaster, it's fairly barren. So you might want to add things. You might add waterfalls, add birds flying through, other things. There might be merchandising opportunities or marketing opportunities in that. So we
I could have anything, couldn't I? I could have like a blimp flying by with, drink Coke on the side of it.
Exactly.
Okay.
Or you could have a stage set up with the latest release from some band playing on the stage.
Right. So Taylor Swift's playing in my virtual space, which I'm experiencing on a roller coaster. What about sound? Am I going to hear her, or am I hearing the roller coaster?
Well, sound is an interesting thing. Initially, our approach was to not add any sound because the sound of the wind through your ear, across your ears is important for that immersion. But there's certainly a potential to add sounds.
So it'd be a mix of both then, wouldn't it?
Correct.
Yeah.
And that's actually quite difficult to achieve, but to mix it really well. But then you can add things like an archway of rock that you go through. So you need to make sure that whenever you have a turning point in the roller coaster, there's something interesting to look at, because you want people to look around and just to be immersed in that environment.
So everyone's experience on the roller coaster would be different. Like the guy at the front is having a completely different experience in two ways. Firstly, he's further along your 3D model, like he would be through the arch. And then secondly, he has the individual experience compared to the person next to him. The woman next to him won't be looking left, he might be looking right. So we've got my head and where I am in the ride.
Yep.
And we mentioned latency. Like I would imagine that it would be really, really, really important that if I turn, I'm getting that immediacy, because obviously that would cause me to get motion sickness, and also the immediacy of making sure that if I hit a bump, that's all being mirrored at the same time, and you could get that fast enough because of this knowing where you're going bit.
So right, so there's two things. First of all, because all of our vision is pre-rendered, we're simply selecting which frame to show at the right time, and that's predictive. So that we're not reliant on a huge amount of processing power in order to render all the physics to make it look good. So we can have this extremely high resolution, extremely good quality graphics pre-rendered that will be very believable. But secondly, what we do is we decouple, or we'd like to, the headsets aren't available today, but the technology that we're working on is to decouple the scenery update from the camera rotation update. So your head, as you're moving around, and the sensors in the head-mounted display are being used to control the camera rotations, but the scenery that you're looking at, that's effectively the environment map, is updated at a potentially lower refresh rate. What that allows us to do is to update the camera refresh at, say, 1,000 hertz.
1,000?
1,000 hertz.
So not like 100 or 90 or 120, 1,000. That's like 10 times what?
Correct. And so this is very important in that some of the main problems with virtual reality becoming mainstream is motion sickness. And motion sickness is caused by a number of factors. We don't fully understand all the factors, but definitely one of the factors is what people call judder. And judder is quite complex, but it has to do with the pixel persistence of the displays. And so what happens is, because pixels are modulated and they turn on and then turn off, and then turn on and turn off, you get this, as you're moving your head around, you get this effect where you get a smear and then a jump, smear, jump. And if that happens at the wrong frequency, it can cause motion sickness in up to 30% of people who use it.
But you can turn an LED off and on really fast. And not only that, it doesn't have a lot of persistency. So is that persistency inherent in the LEDs that they're being used for the displays, or in terms of making the footage come in faster?
It's kind of both. So the problem is, yes, the new OLEDs can certainly do the low enough persistency you need, which is below 3 milliseconds, so around 1 to 2.5 milliseconds persistency. The problem is that the driver chips people are using are designed with the expectation that people are going to be running at up to, say, 120 hertz. So the driver chips don't drive the displays at the rate that they can run at. The second is that if the information you're putting on the pixels is only at 60 or 100 or 120 hertz, then you don't make use of the reduced persistency.
So the only bit of this jigsaw puzzle that isn't in existence at the moment is this decoupled thing, because I've seen televisions like a non-VR helmet television that can run at pretty high hertz, maybe not 1,000, but I'm probably sure I've seen 500 or something.
Yeah, around 600.
600, right?
Yep.
Okay. So we're not in science fiction land. Like,
No.
it's possible. It's just you need conceptually or physically to break apart those issues of, it's not like I'm rendering it. It's I've got a texture map. I'm just going to display that view on it.
Correct.
And getting that ready to go can be buffered because I'm on tracks and so I'm not going very far, and B, you can kind of like just presumably write the software so that it can throw away what it doesn't need and just go with what I'm doing, I guess.
Yeah, in the case of what we're doing, you don't need to throw anything away. But for gaming, you could actually do it for real-time gaming if you rendered about 10% greater field of view than what you need, because there's a couple of constraints, and one of them is how fast you can turn your head and your eyes, which is actually quite fast. I've forgotten the exact speed you can turn, but it's around, and I have to check this number, I think it's about 600 degrees a second.
I was going to say, it's particularly good if you're being scared the living daylights out of you because you're in an F-16 going through a rocky outcrop over the Grand Canyon.
Right.
But yes.
Yeah, so given that you can predict the fastest that most people can move their head and eyes together, you can actually work out at, say, 60 frames a second how much extra field of view you would need to have this decoupled approach, so that you've got the scenery ready as they turn. You've got that extra bit needed so that they don't see the black curtains at the edges.
Just speculatively speaking, I know that your proposal looked at it as an immersive VR helmet rig that would take me to the Grand Canyon, but there's probably nothing stopping this having AR applications as well.
Correct.
Though, of course, now you've got Taylor Swift playing at the concert that I can see at the park I'm at.
Yeah, and that's a really interesting area. I think there's a lot of work going on with Microsoft's HoloLens, with the work Professor John Walden's doing on his DigiLens, and with what Magic Leap are doing, where they're using these holographic approaches. One of the very cool things about these holographic approaches is that it moves the weight away from in front of your eyes to at the side of your head, because they use these optical waveguides and holographic optical elements to get the lensing effect. It means that the actual display components are by the side of your head, where the weight is here, and in front of your eyes, essentially just a thick pair of sunglasses. And I think that's a very key thing in terms of, first of all, from an artificial reality point of view, to be able to see through the lenses, and but also, an augmented reality point of view, but also in terms of the comfort of the people using these things. One of the big issues that a lot of the sort of veteran VR people laughed at is they know that people aren't going to sit on their couches at home with these big, heavy goggles on head-mounted displays on with all this weight in front of it. It's not comfortable for long periods of time. And so this is one of the areas that has to be solved, is that the weight has to come away from the front of the face and be put somewhere else.
I must admit, the number of VR experts I know who don't have straps on the back of, say, their Gear VRs and just hold them up, put them down, hold them up. They just never sit there with it on for an hour.
And that's interesting. We actually worked on a project that never came to fruition, but we were trying to shoot the 2014 Super Bowl with some VR capable cameras, panoramic cameras, and the project was to have people at a bar, if you were down at the bar with your friends, that you could be able to just hold your phone up and you'd have streaming access to these cameras. So rather than hold it to your face, you just hold it out here and move around, and it would let you sort of investigate the different viewpoints. And the reason why that was interesting was because it meant that someone like AT&T or Verizon could ship out these very inexpensive, potentially very expensive VR viewers, or you could just have your phone and you could have access to this or your tablet, and you just hold it like this. And so we thought that as an interim solution, this would be a way to take things mainstream without people putting bulky headsets on.
Yeah. Well, look, thank you so much for taking time to talk to us. Michael understands this technology so well. I really appreciate having him come in and talk to us. Thanks, man.
Thank you.
Appreciate it.
Cheers.
So it seems kind of weird to leave that interview at that point and, of course, not be, showing you a working system. But I think it's amazing that Mike is willing to discuss it. Of course, we didn't really get into the interview. Mike actually has patents covering a bunch of this stuff. So if you're thinking of that he's just given you this multi-million-dollar plan, he isn't actually that interested in running that tech because he's kind of a serial entrepreneur. But yes, they have patents and a bunch of stuff now securing the rights to doing the stuff that he was talking about. But I will say it's a really amazing application of VR. And of course, there are a bunch of other considerations that we didn't get into. Obviously, things like the headgear being attached to the roller coaster so you couldn't lose it, or if you did take it off for some reason because you freaked out, it wouldn't be dropped or let go on overboard. Actually, in the early days, he even looked at doing the whole thing with wireless transmitting out, but there's just no way you can get the latency down no matter how good Wi-Fi is even today. So it's a very concrete proposal to do something really, really amazing, but it just such an interesting discussion. It really got me thinking about some of the ways that VR could be treated differently and just breaking out of the traditional business models. Of course, the most immediate business model that I have myself been pushing is the idea of using it for trailers, just simply being able to have a system of trailers that you could download and use Google's Cardboard with a phone in it and have a look at some really interesting immersive environments, because in that scenario you have the marketing budget for the film, the reality of people having the phones, and you only have to give them the cardboard. But there are these other specialist applications where you can afford to have like 100 dedicated rigs and really have an amazing business proposition to add a whole new dimension of entertainment to something that otherwise, as Michael said, has kind of been tied. That idea of refreshing with tech, something that's a bit tired, is really, really interesting and relates, of course, to just how far this stuff can go. So I wanted fairly early on in the term to just sort of expand your horizons of what it is that we're talking about so you can see the kind of range of places that it can go. Well, keep your questions coming in the forums. I'm really looking forward to showing you some of the hands-on stuff that's come out of our NAB experiences, but more of that in future weeks.